All right, so I'm back on my story engine work today. I haven't actually touched this since last week, except maybe very slightly. But I just spent the last week working on other parts of my code base, audio processing stuff, and the podcast rendering, the podcast video, audio visualizer, and stuff like that. So I just haven't touched this much. So I don't have a extremely clear memory of how all of it fits together exactly, but I do know pretty much where we're at and what I want to be working on. So let me just get a quick refresher in my head of where things live and what features we actually sketched out and stuff. So right, so the only thing I've done off stream is on stream we built this step function for the new virtual machine, and it handles the very basics of flowing from node to node and the interesting kind of non-determinism feature that I have in this model, which is the fork. So we implemented the fork, and that comes with some modes. Now here they are. So deterministic mode, fork mode, non-deterministic mode, await, and resolve. Those are the 5 modes that the system has right now. And that's all working. And then what I started sketching out or building towards is, since I have a step function, I want to be able to do that in a loop to make a run function, and that's sort of working. So when I'm in debug mode, I can see what happens one step at a time if it still works. Okay, nice. And if I'm out of debug mode, it runs through all the steps and it doesn't show the although I don't think I actually finished this. Yeah, so single step. Let's I was reconfiguring my debug option, so I think I want to call it single step instead of debug for anywhere where it's doing the logic of not running ahead. We'll do the single step, and anywhere where it's doing fill the debug info, we'll call that the trace. So this right here is trace. This right here is trace. This right here is single step. So I can do single step 1, trace 1 to get that behavior. I can turn off the trace. This will be kind of useless. Now I can't see the trace. Or I can turn on the trace and turn off the single step, and then I would get this. So it runs to here. So that's what I was trying to rearrange there. It's another small baby step towards being able to actually debug this virtual machine while it's running. Probably I want to be able to have a mode where it's like the trace goes to a log while it runs normally, instead of it being on the screen, so that I can see all the steps that happened. So I'll keep that in mind, but I'm not going to do it yet. The other thing I'm trying to deal with is that method you see is supposed to say all of this whole line, and it's cutting off after 7 bytes for some reason. I don't know what that's about. So that's what I want to debug first. Let me pull up remedy. Yeah, okay. So the question is, why when it goes to show so it gets here, it gets to show data. And so that's the end of the step. Since show data is not 0, we have some show data. We mark this as a moment where we have a result. And then what's going on inside that pointer? I guess remedy won't show this as a string, so I probably have to do it like this to get a string. Yeah, so that's what it should look like. And here's my mistake. I said lit here. That means it thinks it's getting a literal. That should be a C string. Okay, so get the string from a C string. Looks like that. There we go. So it runs to that message, and then I can continue. Okay, that's progress. Turn that off for a moment. And let's see, other things I noticed. I want to center the verb, at least the continue verb. Whoa, that's not ideal. Okay, what just happened there? Here they're lined up on the left. I'm not sure what that did, but that's annoying. Something fishy with how my layout system is working. I think that must mean that the space, the total width it has for laying out is a fixed number, and then it lays out the first chunk to the left, and it lays out the second chunk centered, and puts them in the same layout. And then I look at the size of that layout and center it, which is not great. What I would rather the logic be is that these verbs are centered. This verb here is centered within the box that is determined by the width of the text that we do have, but I don't have that logic, so I'll have to think through that a little more carefully. BYP, where does the VM fall in terms of FSA, PDA, TM? So the idea here, the VM is a Turing machine. It's Turing complete. Like it doesn't actually have enough to be that yet, but it will be. That's kind of what we're going to do today. Is we're going to turn it into a stack-based virtual machine, so it can do arithmetic and branches and loops and stuff. And it's going to operate on. Excuse me. I think it's going to operate on a like a dynamically typed like scripting style environment. So it's not going to be like, a chip emulator or something where I'm actually setting up a a memory block and addressing into it. That might be where I want it to go someday, but I've gone down that path once with this project already, and that didn't seem to make a lot of sense. I think what makes more sense for this project is to treat it like a scripting language, so that I can get past so I can get the easy parts, so I can get past the annoying parts without making it hard. I can make some stuff that would be harder otherwise to program, like I would need a full-on compiler. With the scripting language, I can avoid a lot of the annoying stuff. But there's a twist, which is this fork, verb, and block. And Gate participates in this, but it's sort of a just helper. Fork, verb, and block adds a twist to the VM that in a way makes it more powerful than a Turing machine, because it's now a non-deterministic Turing machine. So what this part does is when the machine is executing, if it reaches a fork, the fork has a special control flow meaning, which is instead of normal nodes, which just have one path forward, or branches, which have two paths forward based on a Boolean decider, the fork can have an arbitrary number of steps forward, and there is nothing inside the machine's logic that determines which path to take. So it can say, like, you get to a fork and there are 3 branches, essentially, but there is no if. It's as if it's undetermined, right? And so the idea is that any of these could happen, and which one you actually want to do is not a decision that is made within the machine itself. So that leaves the idea of how you make that decision as something to happen outside of the machine, whether that be from a user interaction or from a separate algorithm that drives and makes these decisions, like an AI or some other kind of generative decision making algorithm, or just random, right? It could be random. You could also do more fancy stuff with it, which is to say, like, when you get to a fork, remember all of the possible paths and then continue executing them. That obviously starts to slow down, because each fork you reach will multiply the number of essentially parallel threads you have. And so then you would truly be running like a non-deterministic Turing machine, which grows exponentially the complexity of executing the thing. But if you wanted to, you could do that. You could. The idea is that the virtual machine itself includes this forking possibility to just look down at to encode the idea that at some points multiple things can happen and they're all valid, and leaves it up to whoever's outside the machine running the controls to fill in the meaning for that fork, essentially. But when it reaches the fork, what the machine literally does is it executes each of the paths until it reaches a verb or a block. A verb tells it this is a direction the machine can go, and a block means this is a dead end. So when it finds a fork, it looks down all of its paths, executes all of them, and gathers up the possible verbs, and that's what it exports to the controller outside of the machine to make a decision about how the machine proceeds next. And so the machine has capabilities like rolling back its state changes and stuff so that it can go back to the beginning of that fork and execute all the branches with the initial state from the fork rather than like carry it. When it goes down one path, if some variable changes, it doesn't want to carry that variable change back to the beginning of the fork. When it goes back to the beginning of the fork, it restores its old state. Okay. Now this layout thing that I hit, this is not something I want to get bogged down in, but I want to think if there's an easy fix. So what's happening is I think the verbs need to be in a separate layout pass. Let's see if this works. And so we want to set up the default style to be the same. Maybe I want it to all be centered just to make this easy. This leads to problems though with the scrolling. Now I don't want to get bogged down in this. So, like I said, I am not quite happy with the layout system. I'm gonna have to do something a little better. But this is just gonna have to. I'm just gonna have to live with the funkiness right now, where it looks like this. Okay. And then it should get stuck. Yeah, okay. So, a couple of different things I could do today to make progress. There's the fact that this is not a rich enough way to specify the strings, right? So, probably what I want is when it says show here, What I think it really needs to be doing is it needs to be going to a built-in function kind of thing. Or like a, yeah, it needs to go to like an external function call, right? It needs to say, hey, I don't have this interpreted as a instruction, but we want something that like makes some kind of determination to return some data. Or, you know what I could do? Let me see. Yeah, data is just a void pointer. This could be... Okay. I'm going to rename show to out. Okay. And then here, instead of preparing it as an element text in this higher level thing, it's just going to be called out data. And it's going to be up to the... It's going to be up to whoever's using the machine to determine how they use data when it comes out. So that doesn't have to be just a plain old string. It can be whatever we want it to be. And then, in order to make this easy to specify, what I was doing before is I had this whole system where I had a script for separate functions that that would then I would put like the intro like this. But I think instead what I want to do is I want to switch to just saying like, let's put the identifier here. We'll treat it like it's linking. So this is the intro. This is the name for the thing that I want to have happen here. And then I'll have some slightly easier way of specifying these. That was, the other way was too clunky. So I guess I'll put it in a separate file though, so that it is not like mixing content with code. This will be like, well, let's see, what is the fancy string? Request h proc. Yeah, I think we just delete this. We take this out. Let's start catching up on my changes real quick. To do. Okay. So before I do the new one, I think I can tear out this entire idea of a story proc. I think that is gone. So these will be renamed to literal and identifier or something like that. And they'll just both contain a string now. So these will be like, say, here's the fragment kind, Here's the string. Internationalizationalist. Hello, welcome. How are you doing? Hopefully that'll do. Sterlit. Okay. These will both look like this now. Now the difference will be QU story fragment kind, literal, and identifier. I'm doing pretty good. Story fragment equals, yeah, that should do it. But why does it not do it? Right, so the literals will still work the same way, but if we get an identifier, the way we want to render that is now there's going to be, and this is where this part comes in, this function over here, which we're just going to set up in a separate file like this. It's going to take the fancy system, and it's going to take the identifier. And so instead of calling into a procedure pointer, we just pass the identifier down. Right? And then that header needs to come live in this region. And then we have just this one spot where all the content will go. So instead of having a bunch of pieces, separate files for the separate pieces of like rich text, fancy string data, all my fancy string data for the game will have to live in this one file now, which might be a downside. But it could be an upside because I was getting kind of annoyed of having to make so many files that had such tiny little pieces of content in them. So we'll see. So the idea here is that I can pass down an identifier, and then I'll just have a list of all of my content like this. and each one will have its own identifier. And that way I can do the rest of this like a regular old fancy string procedure in the old system. So let's pop over here to the fancy string API so I can remember how to call to it. Let's say the fancy string I want is, well, let's take a look at something here. Paragraph space width align. So we set up some defaults. We do a paragraph on each element automatically and a page break between them. So I don't need to do my own paragraphs or elements. What I'll do is I'll just say fancy string f something like this, right? And so then where is that assert 0 that I put down? Yeah, here it is. So now if we get back out data, then I will assume the out data is an identifier. How do I want to do this? QU element text data story fragment. Yeah, that's a good use for story fragment. So these will take a fragment. So instead of putting an element onto the thing there, I'm going to go identifier equals straight push copy run arena, and then the new elements fragment run arena story fragment kind identifier Now that's not the best way I could do it, because I also know that I have all of these story fragments sitting in a list somewhere. Wait, do I have that? Yes, because I have the key properties. Well, I guess that doesn't work. Yeah, I mean, what I'm doing works, but the way I was thinking of making it better actually doesn't work. So those just print out their fragments. And then here, where I save text into the elements, I'll just save it into a fragment instead. Kind of annoyed with the verbosity of the fragment function, so I'm going to, instead of typing in a full kind, I'm going to make it be, well, yeah, let's do it this way. So we have this, but let's just throw in the helpers here that take away that giant the giant name of the kind, and we have the literal version and we have the identifier version. All right, so this right here says you give me an identifier and you give me a literal from that. So you're a literal, you're an identifier. And then you go like this. Fragment, arena, QU, story fragment, kind, literal, string. Okay, so that's working. So what that means I should be able to do now is I should be able to start putting the fancy strings back to use like this. QU colors. Dot location. There we go. Okay, so I can actually start writing stuff again, which is cool. Now that that's out of the way, let's talk. I want to commit that as, give me a sec. Okay. Cool. So now let's talk more about the virtual machine again. So we want to look at this. And what I think needs to start happening, if we look at what I can write so far, I can write some text. The player can make a decision, and that takes them down a path. And then I can write more text after that if I wanted. So for instance, I could do if the thief would go to a thing called out, and then the out would go to a thing called join, you are the thief, right? I could do something like this, and this. And this. So that should mean, it should have gone down this verb, and then it should have run this out here. It's before it got to the exit. Let's put this into single step trace mode and see what that's about. So it's now running down the different branches of the fork. Now it's in the await mode where it's waiting for me to determine which branch of the fork I want to take. I click I am the thief. It's now in resolve mode. It takes the wire, it takes the thief node. It finds an out node. And we stop right here. Oh, right. I have to remember. Okay. So here's how I use the must have just reconnected to Twitch. Okay, well, hopefully I didn't drop or anything. Let's make a macro to help with this. So this feels clunky, but that's, I think, because this should really be something that you get through an editor. But I think it's the correct organization. For the system. Okay, so if I do it that way, then when we get here, it goes boom, it goes boom. There we go. So that's how it should look. So if I put it back into normal mode, the way the engine runs now is you get some text, you read it, you press, you go, oh, I got a decision, and then it gives you a thing, and then when you press continue, it hangs because it gets to the end of the game where it doesn't have a graceful exit behavior. Let's fix that. So first thing, when we say exit, let's put the machine into a mode called off. And if the machine mode is off, and we go like this to exit the loop. And let's see, I guess what I'll do is that. When does smrun get called? Okay, so how does the loop end here? Output quit. Tick and draw output. Okay, so that's an app update and render. Does the app state... It doesn't remember... Oh, here it is, the output. Okay, so I should have a function in app that's like app quit. And what app quit would do is say that at the end of the frame, maybe this is a frame accessor, frame DT. You'll reach into the output and say quit equals 1. So if I do F4, it works. If I do, okay, weirdly, that's not great. Oh, so it's determined its initial mode, right? Okay, so node putter, yeah, set the machine's mode to deterministic when you turn it on. So it runs, gives me some options. I pick one, and then it runs. Nothing is happening, but it's not getting caught in a loop, so I can at least exit this way. Why didn't it? Oh, so if we hit exit, run result, yeah, off. Okay, so quit. So now it'll say that and then quit. Okay, cool. That works for me. Let's get a little bit deeper. So that's out of the way. That's out of the way. Now this is only correct because we don't have a call stack yet. Later, this exit would be more like return. And so then we would actually want to do something different here. Okay, so wire isn't going to be real anymore. What we're going to put in its place are all of the common operators for a stack machine. So let's look at that. I'm going to want Um, there's a couple ways I could approach this. Let's start with the idea that I want a load and a store and a const. Okay. What I'm going to want is I'm going to want a data table that gives me the info about all these things. All right, so that's going to include an expect path count, a pop count, stack pop count, a stack push count. I think that's good for now. And then we're going to want something like this, which will have a node kind and then a metadata. And what we'll do is we'll have a node kind metadata section for the functions. We need one that's like sm metadata prep. And then once that's been called, we want one that can go node kind metadata from node kind. All right, so what we'll have is right here, there will be a global variable just hanging out. It's like, I am the node kind metadata array. And so when you ask for this, what you're getting is that plus the kind, return that. So then the question is, where does that come from? And what we need for building that, what we could do is say, this is going to be a fixed size array, so we don't need an arena to allocate it. It'll just be hanging out. And then what we want is a bunch of these rows here. We don't actually need to make this globally visible. This can just be like this. Here's our table. And the reason I'm doing it this way is so that the enum here doesn't have to line up with this. So I can put the kind down and have a label for each row built into the text. Basically turning the text into a better interface is the goal there. Um, and then let's see, each of these would be like this. And then inside each of these, we would do where's the metadata struct? Yeah, these. So enter. How many paths come out? 1. How many paths pop count? 0, 0. Okay. So flow, the ret has a 0. I'm going to put all of these into hex mode. Let's just fill them all with zeros to get started. And then the question is, okay, so for each one, what's the flow amount? So out has 1 flow, load has 1 flow, const store branch has 2 flow, fork has an unbounded amount of flow, gate has 1, verb has 1, block has 0. Now, stack. Right now, this does no stack stuff. This does no stack stuff. Later, return might want to do stack stuff. I'm not sure. It would make sense. Maybe to say that it pops one thing off the stack as the return value of the function. Out right now, that's doing nothing. That's just a hard-coded constant that it outputs. Again, you could imagine that maybe what I want to do is pop something off the stack and output whatever is on the stack and then load the constant in from here. But let's see. So load will not pop anything, but it will push something. Const will do the same. Store will do the opposite. It will put something, take something off the stack. Branch will take something off the stack. Fork will do nothing. Gate takes something off the stack. Verb and block don't take anything off the stack or put anything on the stack. Okay. So there's our metadata as a as a human constructible table. Now what we want to do is loop over that when we are initializing the system to turn it into the one that's quick to index, right? So this one is nice, but you index this one by using these kinds, which means you'd have to scan, and we want to avoid that. So we're going to do a loop over all of our table and send it out like this. Table I dot kind equals table I dot metadata. That way, if these get out of order or if I forget some, this continues to work, right? And I can now just count on the names here corresponding to their data no matter what happens. Okay. So here, what's happening is we're gonna go get that metadata. So the reason I did all that was to say that we don't want to be doing this metadata check here anymore. Or like we don't want to have a thing here for getting the expected path count. That might be some information we want to get from all sorts of places. So metadata from node kind. Here is the node kind, there's the metadata. And then we go, what is it called? Expect path count, good, okay. Pull out the expect path count. Now it's using max U8 as the cap instead of max U64. Right, I should initialize it like this. All right, now these things that say wire, something we don't have in here that we might want is just like a true no-op. That way something like this can be the no-op. Now let's start to rewrite these. Instead of pretending like there's a scripting language here and these things called wires, this is going to be like, okay, so this is a const, and the const comes from QU game key thief, and we'll do putter from int right there, since we pass data in as putters in the macro scheme. So to pass a constant integer in, I have to tell it to treat it like an int. And then we've got a const on the stack, so we want to do a store. And for now, when I do the store, I'll just put in the name of the variable right there. So this puts a constant on the stack and then stores that constant into that variable. Same thing here. Same thing here. All right. So let's get this in the best possible order. So fork goes to thief. Thief will go to, and now I just have this annoying problem of needing to specify things in this clunky way where I have to come up with names and chain them. So it might be worthwhile to say like, hey, we want some way to do linear chains of like instructions without it having to look like that. We can revisit that question in a minute if it makes sense. But let's get, so fork will come into there, and this will go like W1, W1, W2. Fork comes into this, and then that goes into W1, W1 goes into W2, W2 comes to here, and then there. Okay. And then join goes to the exit, which we now call the return. But what do you mean too many outgoing paths at enter? That should be a 1. So expect path count, enter kind. It should contain a 1. So, oh, I haven't run the metadata prep function. Yeah, but before we do anything else, let's run that. Okay. That should have exited. Why did that stop working? Thief, it did the out. It went to the join. Well, probably what happened was the no-op isn't in the list. Yeah, I haven't implemented the no-op, so that needs to look like that. It's kind of annoying how I have to always remember to put each of them in. It doesn't like have a default behavior for the control flow. I guess we could fix that. So why don't we try that? Why don't we go SM node default next node equals 0. If node first path does not equal 0, then default next node equals node first path destination. And then all of these things that are doing this just don't need to do anything. If you don't want the default next node, you can clear it out. Yeah, you do that, you go like that, you, and you go like that. You clear it out because you do your own thing. You clear it out because you do your own thing. You clear it out because you do your own thing. I guess you're like a branch, so you clear it out. You clear it out. You clear it out. You clear it out. Well, no, so if we are clearing it out, it should be in this section, right? Yeah. So that way, when I do this and this, there we go. Now it all flows correctly again. And as I add new instructions, I don't have to remember to constantly be talking about their control flow being that they go to the next instruction. I only need to specify control flow as overriding the default, which the default is that a node, the most common case is a node has a single next pointer and we go to that. All right, so now let's work on the stack, which is these three guys, right? So I guess an easy place to start would be with const. What we would want here is the ability to do something like SM machine val stack push. Here's the machine, and the value comes from the node's data. So that would look like this. SM machine val stack push. SM machine void data. And so our machine is going to need this new thing called the value stack. Yeah, so let's go like this. This is extremely fatty. It is not the way you would do this if you were trying to make a virtual machine that ran fast, but that is not indeed what I'm trying to do. I am trying to design a particular semantic for it. So it's probably good to do it this way. Val stack, val stack. I'll keep a val stack count like this. And so this is just going to be allocate a new val stack value. Val stack free. If val is not 0, then we pop that. Otherwise, we push onto the machine's arena a new val stack node, and the data goes there. It gets pushed on top of the val stack, and the val stack count goes up 1. Okay, so there's the push. And the other thing we need to be able to do, somewhere around here we have the idea of a snapshot, right? Or do we? Run result verb, thought we did. Fork, oh, we call it fork save and fork restore, but we never actually built, okay, got it. We never actually built any save and restore stuff because we had nothing to save and restore, but now we do. We want to be able to save and restore the val stack, I think. The other thing we could do is we could say the val stack should be empty when we reach a fork. And when we reach a verb, and then we wouldn't have to restore it. Because if we ensure that we follow that restriction, then the val stack is empty, and when we restore to it, the val stack will be empty. So the val stack only grows and gets used up for computations, but it doesn't like carry stuff through fork control flow. And I kind of like that because that doesn't feel like a good use of the val stack anyways. The only way that could be useful is that if you start wanting the machine to run faster, and so you're putting stuff on the val stack as local variable storage. But again, that's an optimization thought process. And so I don't want to prep for it right now. So actually, we don't need to save and restore the val stack. Instead, what we do is when we reach a fork node, we're going to assert that the machine's val stack count is empty. We'll do the same thing when we reach a verb. We can't do that here, but what we can do is say that when we reach a gate, it should be 1, because we're going to pop one thing off. With a gate, we're going to pop one thing off the stack and use that to make a decision, and that decision can be a block, and so the block will require 0. So this should be a 1, so that after the pop, it always has an empty stack. And then this one is the actual block that should have an empty stack. So the reason for these is these are the things which can, anything which can take us to fork mode needs to start in val stack count equals 0. So if every time we reach fork mode by running into a fork, we have a 0 here. And every time we go back to fork mode from the blocks and verbs and gates, we also have 0, then the val stacks don't need to be restored, right? Like their empty stacks are equal to each other, so we're just saying that these will be equal to each other by making them be empty, and that should be good enough. That should be good. We should still be able to program the machine in all the ways we want to with that restriction. So hopefully that is good. And now what we want to do is we want to be able to pop things off the val stack. And for that, we would need another function like this. Val stack push, val stack pop. Okay, so to pop off the val stack, first of all, there's a default value of 0. And then if the machine's val stack is non-zero, we will grab the val. We will set the result equal to the val data. we will pop the machine val stack and push that onto the free list, and we will decrement the val stack count, and then we will return the result. Okay, so store and load are almost things we could do now, except that we need a variable system, right? So I can do const, pretty easy because I just put the data here. But to do a store, I would need to go data equals sm machine val stack pop, right? So there's my data. And the question then is, where do I put the data? And the answer is, well, I would look at the identifier attached to this node and treat it as a global variable and store it into a global variable system. So let's go make a global variable system. Again, not trying to make one that's actually like well engineered to be fast for long-term use. I am just getting the semantics up and running in order to play with them. We will worry about how to use better data structures and algorithms in future passes if I like this idea in the first place. So with variables, what we will do is we will say we have a queue of them, like a list of them. And when we assign a variable for the first time, or whenever we assign a variable, we'll scan through the list. If we don't find a match, we'll create a new one and give it that name. And then that means we need something like variable sm machine variable assign, let's just say variable, get the variable, and we get the variable from the name, so we need to get the name. Now the name of the variable lives on this node as a C string for now. So our node's data is a C string that names a variable. We look up that variable this way, and then we can set that variable's data to the data we popped off the stack, right? So we use the current node's data to find the name of the variable. We grab that variable from our machine, and we set the value inside that variable. So the first thing it'll do is it will scan all of the variables it already has. And see if any of them have an identifier that matches the one we're looking for. And so that's the right one. So on to the machine arena. We create the new variable. We set its name equal to, I guess we better push a copy of the name. We don't know if for sure if the name we got passed is gonna last forever or not. We might be accessing variables from temporary strings here. And then then we want to stick that into the machine. So we created a variable, we filled its name, we stuck it into the machine. It defaults to having a value of 0, and so then we return the new one, but that should be in the list for future passes to find. Now, if we finally want to implement load, load will go do the same kind of thing, grab its variable. If the variable didn't exist, it'll create a new one and call it 0 right there. And then and you know, later we might want to say, hey, don't spawn new variables on when you're trying to load from one that doesn't exist. Call that an error or something. But we're not worried about that yet. So here we do a stack push using whatever data lives inside that variable, right? So here we did a stack push of the data attached to the instruction node. Here we're doing a stack push of the data attached to the variable, where the variable was loaded off of the name attached to the instruction node. So we have this way to have an instruction that encodes the idea of looking into the value of a variable. So now I've got global variables loading and storing, and I can put constants in them on the value stack. So now what we need to consider is, do my variable values restore? And that we cannot possibly cheat our way out of the way we did with the value stack. I'm probably going to take a 5-minute break, and when I get back, I'll work on that. So let me set up my little note for people. I'll be back in about 5 minutes to work on saving and restoring variable states in the virtual machine. There we go. All right. So we need to figure out how we're going to save and restore variable states, right? That was the next task. That's going to have to live down here in fork save and fork restore. And if I was going to build like a super robust version of this, I would already have done a different variable data structure, right? This variable data structure is already just an experimental hack. Or to put it another way, it's something I've put together in the way I have. I've chosen this data structure because of the fact that it's so easy to make it get done today and to make it correct today without overworking. So whatever I do to save and restore it is going to be based on this. And there's no point in worrying about if this is less than ideal, because I'm already going to have to change the data structure that I'm saving and restoring. If I was going for performance, I would be changing this, and so I would have to change these anyway. So I want to minimize how much I burden myself here as much as possible. So the way I'm going to do that is when I go to save, let's start off by making a fork save struct type, and I'm going to have it contain its own list of variables like this, and we're going to have one of these living down here for now. Okay. So when I call fork save, I'll be filling this with the state from the machine, which so far just means the variable first and last. And when I call fork restore, I'll be reading off of this back into here. Okay. Now, since I'm going to be creating variables, and then when I save over the fork save, I'm going to be clearing out the ones that exist, I might need to be able to free variables now. So when I allocate a variable up here, I was just assuming that I could push one on. Let's say I need a separate variable alloc function and a variable free function, just to isolate and simplify the problem of dealing with the free list, since I'm going to access it from multiple places now. So this is going to become variable free if the result is not 0. Stack pop the free list, otherwise put it there. And to do the free is just going to be to stack push the variable onto the variable free list, right? So this is now result equals sm machine variable allocate machine. So there we go. And then when it becomes time to do a fork save, and by the way, the reason I'm putting this in its own struct is that I know for a fact that eventually I'm going to want to have more than one fork save around at a time. So if I have more of them, because I'm going to end up in situations where I fork, and during looking down the branches of the fork, I hit another fork, and that ends up building this tree thing, which we talked about last time. I'm not building that out yet, but that's a possibility that I'm pretty much confident I'm going to want. If I continue with this model and I keep liking it, the fork tree, the tree of fork saves will become the way I want it to work. And so in order for that to be possible, I'm just sort of preemptively organizing it into its own type, which I think over time will evolve to the point where I'm just dealing with a fork save pointer here that kind of gets allocated here off of a, another free list or something. And so I'm writing it preemptively to work on a pointer to a fork save, even though I know I just have one like hard allocated version of it for now. Now, the first thing I'll do is I'll say whatever's in this fork save, because of the logic of the way this works, whatever's currently in the fork save, I'm just going to free it. So we're going to go for each variable living inside the fork save. Let's do a free, like a free form for loop. We're going to go look at the first in the queue. If the var is 0, then we're done. You can break. Otherwise, let's queue pop. So we take this off the queue, and we variable free that variable, so it goes on to the free list, right? And so there we go. We freed whatever was in the fork save. And we will want a free in the future, but it won't be coupled in with fork save anymore, right? The time when something gets freed will no longer be to clear it out for use again, because there won't be a fixed slot. But this is a concept we do in fact want. It's just right now it can be welded in right here. And so then what we'll do is we'll do a loop over the variables inside the machine. Right, so for each variable in the machine, we will allocate allocate one variable. We'll stick it into the fork save variable list, and we'll set the data of save var of the saved copy from the one that exists. So we know that these are placed into the fork save in the same order as they live on the machine, and we know that they don't change order on the machine because we made them a queue instead of a stack in the first place. So the order from the machine is fixed. It can grow, the list on the machine can grow, but it the order on the list of the order on the machine can grow, but the head end will stay in the same order. And so these can just be lined up by being in order. And then when we want to go and restore, all we'll have to do is a loop where we're visiting nodes on both sides at the same time. So we'll have the write variable will come from the machine variable first, and the read variable will come from the fork save variable first. And as long as they're both not 0, we can keep going. We will increment both of them together. And then we will write the date into the wvar from the rvar like that. Right, so we're reading off the fork save, writing into the machine, everything up to the point where we got there. Then, for as long as the write variable is still not 0, which could happen because this queue can grow. So really we know that this one can't, like this one always should be enough because the write var can't become 0 early. But as long as there's still more wvar we haven't set, we want to set them all to 0, you know, as in the default value. Make them as if they haven't been touched. So it's equivalent to if we touch them again later, it will look like they weren't touched. This would be like if we had a dynamic typing system and we just nilled them all out. But since we don't have nil, we have clear to null, right? So that's the restore logic. Cool, so that's all up and running, which means if it works, we should be able to write to a variable and then, well, we can't branch or do anything that, we can't actually see anything come out from the machine based on what's in the variables yet, unless we do something like log the variables when we store or something like that, or have a log variables node in here that just tells it to drop all the variable values for us. And the other thing we don't have is there's not going to be any proof that the restore is working because we put the verb at the head, and then the rest of this is just a deterministic series of operations. If we put those inside the non-determinism, then what would happen is we would set the player character several times along the way, right? So I'm trying to think of how I want to do this. I initially said it would be better to put this here, but I'm going to change my mind. I'm going to say fork will flow into W1, W2 will flow into thief. So we're moving the verb down to the point where it's after the store. Fork will flow here, W2 will flow here. Fork will flow here, W2 will flow here. Let's get these lined up again. Okay. So then the other thing I need to do is I need to be able to log this out. Let's set up inside the story machine just for now like a log function. that's just going to print straight to standard out to make life easier. Maybe it'll print a log emit f, right? We could do that. Do I have log accumulation set up here? No. Let's see, my fatsat test does use this, so maybe I can use that. App update and render. Begin logging. Okay. Right, so this needs to go out to the thief, beast slayer, and archaeologist. Okay, so it still runs to completion without any problem, but I can't see any of it. So let's build that log. So what I want to do with the log for now is just log emit f. Yeah, I can log emit f. Variables. Log emit f. The name of the variable equals, and then the value. And let's have the machine do its log when it reaches fork mode. How do I want to do this? Fork restore. Okay, so whenever it reaches a verb, yeah, I'll have it do that. Just so I can see what I think is supposed to be there. Nice. So check this out. If we look here, game key. Yeah, thief, beast slayer, and archaeologist 1, 2, and 3. So it went down each path, and then when we selected this one, it went down that path again and set the final variable to 2. So that's cool. It is in fact apparently running a variable system here. The other thing we could check is what do these look like after the restores occur. So after you do a restore, log your state for me. Boom, boom, boom. And here after each restore it to 0. So that makes sense. The first one, it's empty because it hasn't, when it first restores, so it does a restore for, let's look at the fork. When it first reaches the fork, it saves the fork, and then before it does each branch, it does a restore. So it saves and restores itself redundantly once because that's easier than eliminating the redundancy. We wouldn't actually need it to do that. It could realize that if it's just saves, then there's no need to restore. But it saves here, restores to run this branch of the fork, restores again to run this branch of the fork, and restores again to run to this branch of the fork. The first time it restores, no variables exist yet. After it's run this, player character becomes an existing variable, but it gets the value 0 because when we restore to the point where this didn't have a value yet, right? And then after this, every time it restores, it's putting that variable back to 0. So I think that looks good. That looks like it's working the way it should. So this is global variable load and store and fork save for the variable states. Cool. All right, so what else can we do? Also, how am I doing on time? Oh, awesome, I've still got like 30 minutes. Yes, so we've built the value stack. We can now do creating variables with storing and loading and putting constants into them so we can get numbers, whatever numbers we want into them. Let's now do some logical operations. So here we're just going to be generating tons of these. Let's start with arithmetic. So there's going to be add, sub, mul, div. We'll assume that it's all integers for now. Mod. So there's arithmetic. We might also want unary, so negate. Let's fill all of that in. So store, here we go. We want each of these add, sub, mul, div, mod, negate. They each get one outgoing path, 2 incoming stack values for these and 1 for this, and 1 outgoing stack value for each of them. Okay. And then to implement them, we just go add data 1 sm machine val stack pop machine data 2 data 1. Data 2 is first because it's a stack, so the second operand goes on the top of the stack, and when we pop first, the first time we pop, we're getting the second operand, right? And then we want to get a result, which we'll get out of int from putter data 1. I might say, hey, let's have the ability to do something like this, so we can have like x1, x2, pop u32 or u64, right? So it'll just pop the correct type off, and then we'll calculate the result as x1 plus x2, and then we'll push u64 machine R. Now, is there somewhere else where I was doing a push or a pop that I had to do a cast? No, they've all been pointers so far. So let's go and modify, make helpers on these. Push u64, pop u64, right? Push, pop, very good. And then these are just wrappers that automatically do the putter from int kind of thing. in front footer kind of thing. So there's add. Mul. And so on and so on. So the interesting thing here is when we go, okay, if we're gonna have a bunch of binary operators, for instance, that all look like this, what if we just anticipate collapsing the similarities down like this, and then we sub-dispatch again on the kind in order to calculate the actual R value. Right? We can do something here like protect against division by 0. So there's our binary operators, and we have a negate, which I guess suggests that we actually don't want to be operating on U64s, probably. We want to be operating on S64s. So let's maybe assume that's more accurate. Plus minus times divide modulus, and then the unary operators can go like this. Probably going to end up wanting the same pattern sooner or later, so I'll just preemptively do it even though it's a little extra at this point. Okay. So there's arithmetic. Let's add in some comparisons. So equal, greater than or equal to, greater than, less than or equal to, less than. These, let's see. These work like binary operators. Okay. So we can do a comparison. Now let's do some logical operations. logical operations. So let's start noting these. Arithmetic. Here we have structure. That'll go with structure. This is variables, comparison, logical, conditional, and non-deterministic. Operates on the stack once. All right, so we have two new binary operators. And the unary operator. Okay, so that's all the like basic computation stuff. Let's fill in the branch properly. So conditional, variables, structure, non-deterministic, okay, branch. So the way branch needs to work is it's going to pop a value off the stack. And then if that value is true, it's going to take its true path. Otherwise, it's going to take its false path. Okay. So that's branching. Now, fork doesn't do anything. Gate. Gate does something on the stack. Gate is going to take something off the stack. If that thing is true, it's going to flow into its true path, which is its only path. If it's false, it acts like a block, which means it does not emit a verb and goes on to the next step of the fork mode processing. Verb and block don't operate on the stack at all. Okay. All right, so with that, I've got all the basic computation pieces up and running. Let's take the last, 20 minutes we've got here and maybe try to build something with them. So I can use the system so far to pick a path. I don't need these. These were just for testing. Okay, so you pick one of these and it sets your player character for you. Again, I don't actually want it organized that way. That was nice to have for the purposes of testing, but what I actually want is still this sort of thing. All right, I'm just gonna boil it down to that. And maybe what we could do is try to figure out how to solve this problem where I have to manually build these chains everywhere. Fork leads to thief, which is W1, W1 to 2, 2 to 3, W3 to join, W3 to join. Trying to think of what another interface for this might look like that would make it easier to write. That's where my head is going. So instead of trying to test out what I've just built, I'm now doing the probably less intelligent thing to do. It's probably better to just try to use what I've got and write something and see how it feels. See if the computation pieces are working and test fork out more thoroughly. But writing this is such a tedious problem, and I'm thinking there might be ways to do it. I'm going to focus on this for a minute. If I just had something called a T, let's say. So the T comes in, and I'm going to go T equals right, we go like T verb, I am the thief, T equals T right, this right here can be fork, so this can be whatever, like this. And then this would let me just accumulate on that T there. give the intro, or not the intro, give the const footer from int q game key thief t equals smt store player character, and then right, so what could happen here is this could be like node, and then sm path t equals sm fork path f, something like that. This could even be called the fork, right? And then I go get me a path off that fork, get me once I'm holding a path, I pass the path into the instruction that it's going to flow into linearly. So this would go like this all the way through, and t equals sm join. Finally, I joined that back up to the join right here, right? Just thinking through, would this be better? The nice thing about this is now I don't have to rename things. I can just reorder things. And I might be able to eliminate the T if I build off of this plan. So I am the thief, I am the beast slayer character, right? So that goes like that. Archaeologist. Right, so those would look like that. Then the beginning part, which looks like this. So we would need him. We don't actually need to declare this. This can be like this. So sm path t equals 0 at the top here. So we would get something like, could even pull this out just to make all of this uniform. SM entry would go like this. Entries don't take in an input path, but they give you a path. So the entry would do that. It would go sm int t out intro. So out's the intro, and then it reaches the fork, right? So you have a path flowing into the fork linearly, and then here's your fork, and then you build all your fork paths as these linear things. So this is all good. The only issue is none of these. Oh, and we need a join, right? So it's not necessarily the case that your forks always end in a join, so it's not something I want to build into building a fork. Instead, the join would be something like this, and we would have something like this. So we can create no-op nodes just to create places where things join together. like this, I guess, is probably best. Now that's all good. The only question is, what do you do with control flow? What do you do with a branch? Right? So a loop wouldn't be a problem. We would just make like a SM. So a loop would be like this. Loop equals no op. And then you'd go equals node path. Then you go t equals sm ins t da da da, however many times you wanted, and then you go sm join t loop, right? So this would say, hey, take this path and point it back to this node. So now you've got a loop that runs here. So that works. The more interesting question is, what is a branch? If we were to keep writing and say we want to test if you're the archaeologist. So if you're at the join, then you go t equals sm node path fork path node path. Instead of calling this the fork path, I'll just call this the sm path from node. And instead of having SM, it'll just be SM. So this is path from node join, right? And then so path from node join, and then say we want to do an if. So SM branch, right? There might need to be some instructions first to fill up the stack, but then there's t equals sm branch, something like this. So the t flows into the branch, but I guess we need two different paths, right? So we would need like an s up here, then we would go like, here's at t, here's s. So when you branch, you give it the path flowing in, and it gives you two paths flowing out. And then you would build your true path and your false path here. And again, you might also have something like a join no op here and have them join back together down here or something, whatever you needed. I think I might need to go and read the control flow stuff from something like the Retargetable C Compilers book. I think that book has a good API for building these kinds of control flow graphs, and I want to go and read that and see what they say. Maybe there's an idea in there that I could use, but I feel like I need a better API. This down here is clearly not working. Something like this is a step in the right direction, but I'm not sure like if I want all these separate. Like, do I want nodes and paths to be separate like this? Is this useful? Is there a way to do it all with one type that type fits together very nicely? I don't know. So I might need to go and research that next and clean this up, I think. Because if I get this cleaned up to the point where I can write these more easily without struggling with them so much, then I think I could actually build some programs into this intermediate representation thing and test them out. But as it stands, it's so tedious just reordering a couple of instructions that I don't really want to get bogged down in trying to test it until I figure out how to make that iteration a little better. So I think I'll stop there for now because I need to go do some reading and research on how I will, if something like this is the right approach. But this, at the very least, has the property that if I can't find anything else, this feels like a step in the right direction. But I don't know, I think research is the correct next step here. So we're right about at a good ending time anyways. I've been going for about 2.5 hours. That's like a minimum but reasonable stream for me. And so I think we'll wrap up here. If you've been following along and you're interested in this project, you can find out more about things I am up to over at mrforth.com. And you can sign up for the newsletter to get updates about once every month or two about projects I'm working on and podcasts that are coming out and stuff. You can also, if you want to follow projects in video form, you can come to, let's see, where is it? Mr. Forth Programming, where I do polished content about my projects, or the Mr. Forth Unscripted, where I talk about the story engine a lot, just off the cuff. I also have these streams in a video archive over here, so you'll be able to find all the streams related to this project that have happened, and that this one will show up there too. So that's all the stuff you can do to follow this project and my other projects. And I'll probably be streaming again around Friday. I stream usually on Mondays and Fridays. So on Mondays you can catch the story engine stuff, and on Fridays you can catch my Sat Solver and other fun projects. But I also move those days around a little bit. So last week I streamed the Sat Solver on Thursday, but that's generally what I do. Anyways, thanks for coming and hanging out today if you've been here, and I will see y'all around the internet. Bye.